talk will be slightly different than the old talk there. And thank you very much, Costas and everybody who invited me to present some of the techniques which we use for material characterization at Mosaic Group in University of Limerick. And basically, we are not working directly with composite materials. We work with mostly biocomposite, hard soft interface, some of these ceramic materials, and semiconductor materials. And basically, that is, and my own experience is developing scanning probe microscopy for surface modification. And basically, some of the techniques which I will show here, they are one of them is the commercial technique, and then some of them which we built, we are home-built optical analysis techniques. So basically, my talk will be very relevant to the talk which is just delivered before me about Raman analysis. We also do some of the techniques for Raman analysis, but for high throughput analysis. So I will initially start with a brief overview of the Mosaic Group, what we do there, and then some of the challenges in characterizing contact mechanics related problems such as adhesion. So this problem is not only important for composite material, but it's also important for many other materials where more than two materials have an interface between them. For example, hard soft interface, this is also very important. For thin film technology, these adhesion related issues are quite important. And then I will introduce the multimodal AFM institute for high resolution analysis. Basically, this multimodal AFM is hybrid AFM, which is hybridized with some of the optical techniques to give chemical sensitivity as well as some of the sensitivity which AFM has related to the contact mechanics related problem, and then three custom designed high resolution level free optical methods which we developed in the Mosaic Group. So basically, we are material design group which is based on modeling, simulation, and innovative characterization. So basically, since its inception 10 years ago, the group has inspired over 100 million funding through European Union and some of the local funding from SFI and Enterprise Ireland. So basically, we develop solutions for direct industrial problems for analog devices, for both Warner Limited, and also we were directly involved with Cook Medical. And we were involved in 5 European projects where we have developed basically on bio-inspired parts of interface. We developed a night-eye wire for radio pack on night-eye wire with Enterprise Ireland partnership. We have, for example, super resolution chemical nanoscopy for diagnosis and high throughput analysis for drugs. So basically, why I'm here is we know that, as I said in the introduction, that this adhesion-related problem between two materials is common for many material interfaces, which is also quite important for example, fiber reinforced composites. So basically, since it's a heterogeneous nature of the material, is quite difficult for characterizing this material with online non-destructive methods. Even the offline methods, they require quite high resolution, which is beyond the capacity of most of the techniques. So the trap defects modify the local stress distribution, which can initiate cracks in the material, and it needs to be part of the integrated characterization. This should be part of the characterization, should be part of the process of optimization. And buried defects, for example, characterizing them non-destructively is still a challenge and requires the development of new methods. So this the first is a commercial technique which is built by NTMDT, and we were partner with NTMDT because we were willing to have some chemical analysis as well for the materials which we developed in Bernal Institute. So this equipment was designed partly by us. So this is an AFM institute which is coupled with optical microscopy like AFM, Raman, SNOM, TERS, and basically it's a full AFM institute which can do electrical force measurement, addition measurement. Basically it can do kind of surface and subsurface analysis. So some of the examples. So basically, apart from like local conductance map and, for example, spreading resistance analysis and piezoelectric measurements and magnetic measurements, I will show you one of the additional advantage of this AFM is that it has, apart from contact mode and amplitude modulation mode, where the cantilever is usually modulated at this resonance frequency. It has hybrid mode where the cantilever is modulated much lower than the this resonance frequency of the cantilever. And when we do that, basically, since, for example, if we modulate the cantilever at 1 kilohertz, then this is within the limit of the electronics which are nowadays available. And basically, at each pixel during the image, we have a force map of that point, and basically by doing force map we can using some of the contact mechanics theories we can basically calculate the local elastic properties, adhesive properties of the surface. So this is one typical example. For example, this is standard. In many cases this hybrid mode gives us much higher resolution than the normal non-contact mode. For example, this is but this also depends on the surface. This is one image by standard non-contact mode, and this is the image in hybrid mode, and you can see much higher resolution. Here, a kind of height image of the carbon nanotubes on the surface. We can have stiffness map, we can have addition map, we can have current map as well simultaneously. And the bottom is beta glycine, where we have electrical measurements, for example, piezoelectric measurements, and we see the domains. This is the height image, and this is the electrical image, which is, we see ferroelectric domains on the surface. And this is AFM with, in combination with Raman, so basically to get more chemical sensitive information as well. So there was a good lecture before me which has explained what Raman is doing. So basically this is AFM image and Raman image, and this is AFM topography image, and this is Raman image. Basically this is, sorry, not labeled properly. So this is Raman image with two, basically this is the stressed, the shift in Raman peak due to the stress. So basically two image overlap on top of which, and basically shows this local stress distribution. And here we see some, this is again wrong label, so this is nanoparticles inside the silicon nanoparticles, and they show up in this image, and basically we see in the Raman map as well. And then it has, we have tip enhanced Raman as well, where the tip of AFM tip, which is functionalized with some of the metal coatings, and basically it acts as local surface plasma. And basically, if we shine the light at the end of the tip, then under the tip there is local increase in the electromagnetic signal here, and basically that increase gives us enhancement in the local surface enhancement of the local Raman signal. And basically with this enhancement, like the normal Raman spectra, you have resolution of which is optically limited, which is lambda by 2 depending on the wavelength. Here we can get resolution around 10 nanometer, and this is kind of the periodic structure of silicon dioxide that we see the signals when it's of silicon and silicon dioxide. So then this brings me to some of the, this is basically the commercial method where we can use AFM, we can use high resolution AFM, we can use the ability of AFM to probe the contact mechanics, and then we do the chemical sensitivity. We can couple the chemical sensitivity of Raman and SNOM as well to probe the important information about the material which we want to study. So these are some of the methods, optical methods, which we developed locally. This is main infrared in situ chemical imaging metrology. So basically, this was designed for a high throughput analysis of some of the biological materials on the hard interface. Here, these polystyrene beads on a transparent substrate, and basically the advantage of this technique is that you can basically tune between 1 to 20 micrometer wavelengths, and whatever basically depending on your material, you can choose the wavelength which is related to the absorption of the material. Here, polystyrene bead, which has two absorption bands, 3.4 and 6.25, and we see two images related to that. And then we can use multiple beams analysis as well. For example, the two with the same instrument. So basically, we have two images. So basically, two images overlaid on each other. One image is recorded, and this is for the cancer cells and drug as well on top of it. So the one image was recorded at 3.4 micron, and the other image is 2.7 micron, and they are overlaid each other, and you can get contrasting information. The important is that this instrument was designed for high throughput analysis of the industrial application. This can do offline and inline metrology. It doesn't require any vacuum, and this is robust and basically can do video recognition. The other technique which we developed locally, this is also TRL5 stage, where we have coupled confocal optical birefringent microscopy with basically this is a standard confocal microscopy which can accommodate the variation in refractive index, and basically which is birefringent. And we can do three-dimensional. Basically, we can probe the surface of defects buried under the surface. Here, for example, for this example, it's a cellular tape, glue cellular tape onto a glass, and we can see defects which have kind of within nano resolution. You can see defects under the surface, and we can probe them. So the last one is the CARS, basically coherent anti-Stokes Raman spectroscopy. So basically, this coherent anti-Stokes, we use 3 laser beams. And basically, by the combination of 3 laser beams, we can force coherent signal at the anti-stroke reflections. And basically, by choosing the difference between the probe and the stroke signal, we can probe whatever bonds we want to probe. So basically, this is a non-linear process which gives us resolution which is beyond the capacity of beyond lambda by 2. And here this is applied to, for example, the left-hand image is a combination of coupled image of polystyrene or PMMA, where the image was recorded at 2 different wavelengths using the absorption bands of these 2 materials. And here you have a separate image. So basically this can give us, this is again a label-free technique which can give us a 3-dimensional map of the surface and a scale tuning laser between 1 to 20 micron. So that's all from me. So basically addition is a problem which can be controlled, which is dependent on the chemistry, wettability, roughness, charge size, very kind of, it has a complex chemio-physiological nature, and it requires modification to improve. But the extent of modification requires better understanding. Quantitative characterization of the surface and interface properties with multiple techniques at multiple length scale for a holistic and overview is required for a sound understanding. AFM coupled with some of the optical sensitive methods can give us an alternative route for high throughput, high sensitive, non-destructive characterization of the surface. Thank you very much.
Thank you.